Okay, welcome back. Today I'm going to give you most of the time to do your work because you've got a fairly complicated task today. You're going to be trying to take those class documents you've written and build sort of a skeleton of the code. This isn't something that's done too often out there in real development, but it's definitely something that some places will do, and a lot of places will do the opposite, where they build the skeleton and use that to generate the UML diagrams and use that to keep them updated as you go so that you don't have to keep rewriting them. So as I mentioned earlier, these days there's a lot of tools out there to generate UML from code for you. So you'll see a lot of organizations do that if they're going to maintain their UML diagrams at all. You don't see an awful lot of places that want to maintain them from scratch because, of course, that's a lot of work. You basically have to hire someone whose full-time job it is to look through the code base, bug everybody, figure out how it works, and write the UML diagrams for it. That's no fun at all. But some of you, actually, I think most of the teams this time around, also have projects that are very state machine-like. They transition from one discrete state to another. Not all of you have it, and I'll leave it up to you to decide whether or not you're in that boat or not. But many of you, I believe, are in that boat. So we're going to talk a little bit about the diagrams that we skipped when we were looking over the different UML diagrams in that Chapter 5 slideshow, the state diagrams, so state descriptions. So if we can model the behavior of the system in response to external internal events in discrete states, then we should adopt some kind of state machine model. And there are also architectural patterns that correlate a little bit better with this kind of model. But again, I'll leave it to you to look through all the different design patterns that are in those slides. So we're trying to show the system's responses to stimuli and model the system kind of in real time. We're trying to show how the system goes from node to node, representing the system's different states as nodes and then as events between them, as arcs between those nodes. You are probably very familiar with the basic concept of a flowchart, and that's basically a state machine. What I do want to emphasize is that every node has to be a state. It has to be a condition that you are in, like idle, active, that kind of thing. Those are states. They cannot be actions. You can't be in a state like, I don't know, executing the run task. That's kind of a, I don't know, that's a lazy idea of a state. You can have a state like running, but that's also kind of a boring state. But every state should be an event that you are in rather than something that you are doing. And then events that happen, like, okay, you're running and you trip. Now you're lying on the ground. That's a transition between states. So events, tripping, those are always the lines in between. So events should be lines, states should be nodes. When an event occurs, the system either moves to a new state, or you can always draw a line that loops back to the same state. If you are running and you take a step, you're still running. You have not changed state. Okay, so let's look at a state diagram for a microwave oven, a very simple household tool, and yet, of course, the microwave has many states. We start the same way activity diagrams do, with a closed bubble. We end with an open bubble. We recycle a lot of the same UML pieces in this format, which is, I think, a pretty universal format. They've got the states expressed with their name at the top, and then they do have some information about what happens when you are in that state. So that's one format that you could use. You could also put more information on the arcing lines in between. So you're waiting. As you're waiting, you are displaying the time on the microwave. So it indicates what's happening in the waiting state. When a microwave is idle, it just displays the time of day, right? And then in this strange, bizarre example, I don't know where Somerville picked up this microwave that has full power and half power buttons. You get to decide what power you're going to set the microwave to, and then depending on which button they've pressed, it sets the power. Every microwave I've ever used in my life goes straight to the set time state where you specify the timer. So as soon as you hit any time button on the microwave, right, that's the event that drives moving to the timer. You hit any of the time buttons, what happens? It goes into the set time function. If you hit 5, it adds 5 seconds to the counter. If you hit the plus 30 seconds, then actually that might be a different transition, because on many microwaves, the 30-second or the 1-minute button also starts the microwave, whereas the buttons get you into that set time phase. So there might be multiple flows out, at least on every microwave I've ever used. There's the push a number, you get into the set time functionality. The more numbers you push, that time will change. If you want to go 55 seconds, you press 5 twice, etc. Or you push that quick 30, you go into the microwave and it starts rolling right away. And now a state that you probably didn't think about, or a check that you probably didn't think about is the door closed? You probably take that for granted, so don't take things for granted when you're writing your state charts. There are many different little trip-ups like this that if you were just writing the normal operation for a microwave, you probably wouldn't think about, but there is a difference, obviously, in what happens when you enter the time with the door open versus when you enter the time with the door closed. If you enter the time with the door open and then you press start, it won't, because it doesn't want to irradiate you with microwaves, obviously. And note the transition back to the set time function. When you enter a number, it continues to be in that set time state. So these are still events, there's still inputs that are happening, but you continue to be in the set time state as you are pressing numbers. The only way to exit this state and get back to waiting is to do what? Hit the cancel button, right? Not depicted here either. Okay, so let's say that you press the start button and then the door is open, or you press the start button and the door is closed. Note that the pressing of the start button hasn't happened yet, but alright, so if the door is closed, then we're in the enabled state, we're ready to do stuff. The display can show ready. Again, Somerville's microwave is bizarre. I don't think I've ever had a microwave that displays the word ready. I don't even think my microwave has enough like text to display ready, or it displays waiting. Okay, and then you press the start button and it begins. So this is the operation state. This is, I guess, the low effort equivalent of running. And from a software point of view, nothing happens really in the microwave while it's operating, right? That's all it's hardware. It just basically tells the hardware to begin, or diverts power to it, or whatever, and then the microwave takes it from there. The plate's spinning and all that wonderful stuff that happens as your food cooks, that does not have really much to do with the software at that point, at least to my understanding of a microwave. And if you cancel, you go back into the waiting state, or if it finishes, which is not even a labeled event here, it's just a transition because it happens over time with no event occurring, you get into that waiting state. If you open the door, what happens? Well, on my microwave, if you open the door, you get into a waiting phase, basically, where it's just waiting for you to hit start again, and you can't do anything except hit start or cancel. Somerville's microwave apparently goes back to this disabled state, but Somerville has a weird microwave. So alright, anyway, think about states that are maybe difficult to intuit, things like the door being open on the microwave, not necessarily something that users are going to do, but something that you still have to plan for. You might want to plan something like this too. You might want to make a state diagram like this, microwave oven operation. So we've got the operation depicted as one section. We've got our cook, our done, our alarm, our checking. We have different fault signals that lead to an alarm being set off. If the door is ever opened, we go to the disabled state. If the cancel button is ever pushed during any of these, we broadly go to the waiting state. So that lets you kind of depict a large number of states that all transition into waiting in response to the same input, all as one, instead of having like 6 arrows going to waiting, which is a little bit more awkward to read. So this might be a little bit better if you have a system where a bunch of states transition into a single waiting state. You might want to do it like this, where you draw a box around operation and then divert them to the waiting state altogether. Something to consider. Check out some descriptions of the states. You might want to include this as well, a description of all the states separately in the text. You don't want to put this in the diagram because you don't want it to be too crowded. So we'd have like the waiting state. What's happening? The oven is waiting for input. The display shows the current time. The oven power is set to 300 watts. The display shows half power. Again, where does Somerville get a microwave that can show that many keys? Who knows? Stimuli then. You might describe the stimuli. What are the buttons available and the transitions that they incur. So you've got on this microwave half power, full power, one of the timer buttons, that'd be any of the digits, or no, that'd be a number key actually. The timer button is something else. I guess that's like a plus minute or plus 30 second, who knows. There's a door open and door closed. Those are inputs. The latch controls those. They're not inputs, I guess. They're, as Somerville describes them, stimuli. Okay, they come from the outside world. They're not necessarily the user entered, but they do come from the real world. The latch tells you if it's open or closed. So I would actually just describe this as latch rather than door open and door closed, but okay. And you've got start and cancel. Alright, that's pretty much all I'm going to say about that. So for most of you, you're going to need some kind of state diagram, I think. I don't think any of these other slides are going to be useful for us. Nah. Okay, so today you're going to be building a skeleton for your code out of UML. So just a couple general pointers. If you don't want to install an IDE today, then you're free to use Eclipse and just act like it would be in Java. Make sure that everything at least doesn't have any syntax errors, so there's no red underlines everywhere. Everything checks out. That means that if you have a method that's supposed to return an integer, you have to just fill in a return 0 for now so that it doesn't freak out that it doesn't have a return. That kind of thing is fine, but you're not filling in any of the body of any of the methods, so you're not writing any code. You're just specifying the methods and the classes and then leaving out all of the code. But you are linking the different methods and classes together. So if you have one class that has an array of another, let's say you have a widget class and your widget has an array of doodads, then you can include the line that says, array of widgets equals new widget, and then specify how big it's going to be, or whatever you're going to do in order to implement that correctly. So if there are some kind of field for another class, you can instantiate it. You can even write that in the constructor if you want. Otherwise, don't write any code. So you're just filling in the bodies of, or the outline of methods and classes without filling in any of their code. Okay, see you guys in Discord.